Hello, my name is David Thede, lead forecaster at the National Weather Service in Goodland. Myself, Amanda, Wekesser, and Jeremy Martin are happy to share some preliminary findings in the prediction of high-impact dust storms across the Central High Plains. This is part one that began about 3 to 4 years ago. Why is forecasting blowing dust and dust storms so important? Well, it's never been done as far as I know. We've been reactionary when we have dust putting out various products, but we've never either thought about whether it's possible or predictable. So that's kind of neat that we're doing something that hasn't been done before, at least in this part of the country. It's the number one cause of weather-related deaths in the Goodland forecast area, and that's mainly due to automobile accidents. The health impacts, especially on the younger and the elderly, research from around the globe suggests an increased number of hospital visits a few to several days after an event. Symptoms include asthma, bronchitis, respiratory failure, etc. We visited the Kit Carson County Health Department several years ago and talked to the director, and she mentioned something known as farmer's lung. This is a disease caused by an allergy to the mold in certain crops. Farmers most likely get it because it's usually caused by breathing in dust from hay, corn, grass, tobacco, or some pesticides, and that's usually wind-driven. The impacts to our aviation partners, particularly when you're dealing with non-VFR ceilings and or visibilities due to blowing dust. And the results not only benefit our CWA, but our neighbors as well. Here's a look at the wind erosion process. Got a wind profile, X mile an hour wind at the surface, and increasing slowly with height. You've got your molecules of dust and dirt particles. The bigger ones get blown by the wind into the other particles. Some of those break off into smaller ones. Depending on the wind speeds, those get lofted into the atmosphere and carried downstream, and so on and so on. So as long as the wind profile is favorable, that process will continue for hours, for minutes, for a day. Here's a look at the climatology based on an article written in 1976. And you can see we've got a maxima localized from northeast Colorado down into the Texas Panhandle. We took a look at observations by month based on 1,700 5-minute ASOS observations at our sites in the Goodland CWA, as well as Akron and Limon. And we looked at northwest flow events, south to southwest flow events, and then combining the two. And looking at a spike in October as we get out of summer and into fall, a rapid drop off with no reports, no blowing dust events recorded in December. Then we back up a little bit in January, fall off in February, and then we get another spike in March and April as we get out of winter and into spring. Here's a look at the time of day, northwest flow cases, southerly flow cases, and then combined. And as you expect, as we get later in the day with heating, relative humidity drops, more sunshine, warmer temperatures, more mixing in the lower levels, and then it falls off quickly as we get into sunset. So here are some results of the observations in northwest flow, southerly flow, and combined. These are the wind speeds when we had visibilities of 6 miles or less in haze from the ASOS. As we get into the 25 to 30, 35 knot sustained wind range, that's where we get our peak. Very few cases down here below 25 knots. Taking a look at wind gusts, when we combine the northwest and southerly flow, as you would expect. Once we get wind gusts over 40 knots, we get a rapid increase in the number of cases, and then it falls off, and that's mainly just because we don't have that many events with 60 to 70 mile an hour, 60 knot wind gusts. We took a look at relative humidity of the ASOS observations, and as you would suspect, as we get lower and lower into the relative humidity, the case numbers increase. So generally, anything below 60% is good. It doesn't have to be really dry, but the lower the better. We took a look at observations by visibility, and when you combine the different flow patterns, greatest number of cases are up 3 miles to 6. We do have several cases below 3 miles. And then when you look at the aviation, the observations by category, you can see almost 72% of the time when we had blowing dust and reduced visibilities, we had ceilings that were sub VFR. So some good info that you could put into a TAF forecast for the pilots and aviation community. Here's a look at observations by season. We kept out summer during the convective season, but you can see we have a peak in the fall, less in the winter, and then another peak in the spring, and that's pretty much tied to change in seasons. So some of the questions we had way early in the process was, how much wind is enough? How much do we need at the surface and aloft? And from one of the comment modules, it talked about wind speeds of 17 miles an hour or greater are needed to mobilize the dust. And then as a rule of thumb, wind at 1,000 feet must be about 34 miles an hour to keep the dust particles aloft. And they also mentioned being sure to examine winds at 2,500 feet, where the stronger winds allow more dust to be suspended aloft and persist for longer periods due to turbulent mixing. Relative humidity, how high is too high? How much will keep the dirt from being lofted into the atmosphere? Higher humidity, the molecules and the dust particles, dirt particles are going to be probably kind of combined and congealed into bigger ones. X factor, why do we get dust events on some days and not others? Are we missing some parameters? And then the second step we'll see later, we're taking a look at buff kit soundings to look at some blowing dust days and then some high wind, non-blowing dust days. This was fairly significant. This is a radiosonde profile from temperature, wind direction, mixing ratio, and wind speed at Abu Dhabi International Airport. I found this very, very useful and important in our process of the forecasting of blowing dust. Very steep lapse rates in the lowest 2 kilometers, and then a very significant decrease in mixing ratio with height above 2 kilometers. So that was good for us to make notes of and take a look at in the model data if we had an event possible. So in summary, at this point, I believe we can improve our forecasts of blowing dust and dust storms. It is lower that we can predict the actual visibility or range of visibilities or whether an advisory or a warning would be needed. I start looking at wind forecasts for the next 7 days and look at sustained winds at or about 25 knots. Are we expecting any precipitation or snow cover? If not, then I look at soil moisture that is available via the internet. If it's high, but we're expecting dry conditions for the next few days, I'd say we're a go. Again, all we're looking at is soil moisture on the very top layer. It doesn't need to be 2 inches down, 3 inches down, an inch down, just right at the surface. And relative humidity should be generally below 60%, as we talked about earlier, and lower is better. If the answer is yes to all those, then we need to take a look at the wind forecasts at the 0.5 to 1 kilometer layer. And like we talked about earlier, they should be generally double that of the surface, or around 34 miles an hour from the early findings. Then we're going to take a look at the 0 to 2 kilometer lapse rates, and those should be high based on the Abu Dhabi soundings that we looked at. The higher the better, good mixing. That with a wind profile would be favorable. And then when we look above that surface, we want very stable lapse rates or mixing ratios. That'll prevent the dust from being further lifted into the atmosphere and diluting it, allowing for higher visibility. And looking at the 1,700 5-minute observations, we're looking at 30 to 35 knot sustained winds and looking for more parameters to key in on. One day we'll hopefully have this in Forecast Builder to populate the grids. That would help our neighbors for consistency and shift-to-shift changes. So everybody's on the same page using the same process to get the same results. Now we're going to look at part 2, further analysis and results using BuffKit, Sharpie, and Python scripts that Jeremy wrote. The BuffKit data we use Goodland, McCook, Akron, and Limon. 2008 to 2018 were the dates. The dates were broken down by blowing dust events, 6-mile visibility or less. And then we used both null events with winds generally 25 to 30 miles an hour or higher, with no precipitation having fallen past 24 hours. And then events where we did have some either snow cover or some precipitation having fallen the prior 24 hours, and we combined those events. So looking at the sustained wind speed at the 4 airports listed above, for the blowing dust storm events, we did have sustained winds, generally 28 to 35 knots, with the line at 32 or 33 knots. And you can see that's pretty significant when you compare it to all the other windy days. But the wind was much less on the null days. So that seemed to be a fairly key parameter to focus in on. We took a look at the 0.5 to 1 kilometer wind speed. The prior documentation from Comet said we need about double. And from this case, we were looking around 45 knots, or generally 40 to 50 in the dust events that we did have. And then on the windy days when we did not have any blowing dust at any of the sites, the wind speed was lower. And so that would suggest that the wind profile was not favorable to keep the dust lofted and carried downstream compared to the surface. So another key finding there. 0 to 2 kilometer lapse rates, again, like we talked about, higher the better for turbulent mixing. We did have that in the events with dust storms. In the events that we did not have dust storms, but we did have strong or high winds, the lapse rates were a little lower, but not significant. And then looking at the 2 to 2.5 kilometer lapse rate, we want more stable lapse rate or mixing ratios. And we did have that, but not significant difference between the dust storm events and the null events. So in conclusion, based on the preliminary findings so far, we're looking, focusing on sustained winds of 33 knots with 0 to 0.5 to 1 kilometer wind speeds of around 45 knots. 0 to 2 kilometer lapse rates of at least 8 or 9 C per kilometer, the steeper the better. And then just above that at the 2 to 2.5 kilometer layer, we want more stable lapse rates and the lower the better. That keeps the dust that does blow limited to below 2 kilometers and doesn't get to dissipate or thin out in the atmosphere when the lapse rates are higher. Future work, we've acquired an evap pan and a Davis weather station to study solar radiation and its effects on the evaporation process. We're going to take another look at the boundary layer depths and see if there's a correlation between the depth of the boundary layer on the blowing dust cases and visibility, and hopefully provide, when all this is done, documentation to eventually get the results from the study into the NBM to be used by everybody for consistency and shift to shift consistency in producing blowing dust grids. With that, I am done. I appreciate your time. Thank you very much.